This is Physics 2212, Lab 5, Faraday's Law. I'm Andrew Monterroger. Let's get started. So, the purpose of this lab is to test Faraday's Law by dropping the bar magnet from Lab 3 through an aluminum pipe, or a little roll of aluminum foil. The equations this time will be Faraday's Law, which I will go into depth soon enough. The off-axis magnetic field formula, we already calculated this out earlier in Lab 3. I'm not going to go over it. The magnetic force formula, which it would really be IL cross B, the magnetic field, but the reason why they instead have 2 pi r is because we're using basically looped currents, so the L is going to be equal to the circumference 2 pi r. And finally, the last one is going to be the how to calculate a current, which is going to be the EMF over R. Now, to talk about Faraday's law, in short, Faraday's law states that the change in magnetic flux will cause a EMF, some sort of a potential, some electrical potential. And basically it's inducing, and this electrical potential is going to be some sort of a current. So basically that's what we're getting at with that one. The negative sign is Lenz's law, basically saying that nature will always resist a change in flux. This is important for calculations, but for the purposes of the lab, when just trying to calculate the magnitude of the EMF and needing it for the current, it's not that important. It's more important for other calculations you do with Faraday's law. Now, the experiment itself essentially involves me taking this bar magnet and dropping it down 5 times. We have some initial conditions, which I have listed out here. That mu naught value is recalculated from lab 3. If you saw that video, then I screwed up at some point along the line with that calculation, so I basically just recalculated it. We see the system is going to be the falling magnet and a roll of aluminum foil, and the surroundings will be myself, the phone, and the timer. Essentially, what I did was I first used the magnetometer app from lab 3 to figure out the North Pole, and then with the North Pole facing up, I dropped it down the aluminum pipe 5 times. I recorded the videos, scripted the videos to find out the times that you see right here. Then we get that the average fall time was 1.7 or 1.716 seconds. Sorry about that. And we had to make some of the assumptions we have to make for the model would be that the magnet is acting as a dipole, with very safe assumption. Not so safe assumptions is going to be it's an isolated system, and the only force acting on the magnet is gravity. Not so safe assumptions, and we'll see why in just a second. But for now, let's go over to the model itself. Essentially, our model took in some of the data points, the initial conditions, that being the mass, the length of the pipe, the width of the pipe, and the width of the radius of the pipe, and the width of the foil, and use that for creating the aluminum foil, and then use those values to help develop what the magnetic flux would be, and thus from calculating the magnetic flux, we can calculate the EMF, and from the EMF, we can calculate the current using Ohm's law. Do you see that last bit is basically just it modeling the falling of it, having to update having to update things like the actual position of it and the velocity of it. Speaking of which, we can actually see here how the velocity changed with time. We see that to begin with, it had a very fast initial velocity, or a very steep one at least, which would basically translate to a large acceleration before then slowing down to basically being constant. Essentially, essentially what's happening is it's sort of causing it to lower the terminal velocity of it, and that's because the magnetic force is pulling up on our magnet, or really it's pulling up on the top of the magnet, and it's causing the top of the magnet is attracted to the top of, you get what I'm saying. Basically, the magnet is attracted to the top of the pipe, and it is repelled from the bottom of the pipe, causing it to slow down. Now we actually see here the percent error is 31.9%. It's fine, all right. And the reasoning for it being just fine is probably because of those assumptions we made earlier. There were probably other magnetic fields. I probably miscalculated. I probably didn't time it all exactly right, and I could have made some human error calculations. And also things like and I would say gravity and all, but I think that the actual frictional force would be very minimal. But the conclusion is here: what if the resistivity of the conductor was increased to as close to 0 as possible? Lower resistance causes the current to become higher, and thus that means the magnetic force increases. What if there were holes and slots cut into the tube? Basically, if you cut out the tube, you basically cut out parts of the loop. And less tube means less rings of current. Less rings of current means less magnetic force. And why can't you use a steel round pipe? I specified that we use an aluminum pipe or aluminum foil. And this is is actually pretty easy when you think about it. Iron is ferromagnetic. If you were to drop a magnet down an iron pipe, it would just stick to the iron pipe. It wouldn't fall at all. So pretty self-explanatory. But thought it'd be interesting to point out that one. But yeah, it's actually one of those experiments that I think it's really cool to try out at home. Thank you and have a great day.